Good evening, students. Welcome to today's live problem solving session for Analog Electronic Circuits course. We are at week 4, and today we'll be dealing with small signal circuits based on MOSFETs and transistors. So, coming to first problem. So, this is the first problem that we are going to deal with. In this problem, we have the circuit shown in figure 4.1. And there are different values which have been given. So like RB has been given 470 kilo ohms, RC is 2 kilo ohms, beta is 80, VEB. Why VEB?
Because it is a PNP transistor.
PNP transistor, yes. Likewise, VEC is set of 0.2 volts, VT is 26 millivolts, VA is 120 volts. Okay, this much information has been given. This is the circuit that we are going to deal with. We will copy. Paste this circuit over here. Okay, so what is asked in this question? Find the magnitude of small signal voltage gain. So in this particular circuit, when we look at it carefully, it is a PNP transistor, and for a PNP transistor or NPN transistor, what is the small signal gain, that is V out by V in? How much is V out by V in? What was the formula? We looked at it last time also.
Minus GM into
Resistance.
yes, resistance.
Which resistance? Output resistance. So what is the output resistance over here?
RC.
RC. So yes, it is GM into RC. So yeah, it's GM into RC. So how do we find GM for a transistor? BJT, it's
change in
IC upon
change in VB.
VB, or we can write it as IC by VT, right?
Yes, ma'am.
So do we know IC? What do we know? So for here we need, if the moment we find IC, we can simply find the GM. RC is known. We'll simply multiply by 2 and get the gain, right?
Yes, ma'am.
So for here, first of all, we need to find the IC. So how do we find the IC? What is this terminal? In the circuit, what is this terminal? So since here we have the current direction, it's emitter.
Yes, ma'am.
This is base and this is collector, right? So this voltage is known to us. How much is this? 0.6, right? VEB.
Yes.
So that means here what is the voltage at B, VB? See, VEB, if it is 0.6, VE we know it to be 10 minus VB. So how much is the VB? It is 9.4, right?
Yes, ma'am.
So we know VB to be 9.4 volts. Now, so here VB is known, and VB we know, RB we know. So can we find IB? Here there will be one current, other current will be going here. or how can we find RB? Yes, so in this particular circuit, we know this voltage VB, right? It is
Yes.
9.4 volts. We know the resistance RB from VB to ground. RB is how much it is? 470 kilo ohms. So the current IB is VB by RB. So this current will be around how much it is? 9.4 by
2
470.
microamperes.
Is it 2 microamperes?
Yes, ma'am.
9.5. Is it 2 or 20?
Oh, sorry, 20 microamperes. Yes, ma'am.
20 microamperes, right? So this is your IB. Okay. So now what happens? The moment we found IB, how can we find IC? We know the beta.
Yes, ma'am.
We can simply find the IC, right? So IB we found to be 20 microamperes. The IC is beta times IB, which is how much was the beta? 80. So 80 into 20 microamperes. So IC is how much? 1.6 milli?
1.6 milliamperes.
1.6 milliamperes. So we have got IC. So GM is IC by VT, right? That is 1.6 milliamps by 26 millivolts. So how much is the GM that we are getting?
0.061. 061.
0.061. Okay. So gain is how much? It is GM times RC, right? So that
Yes,
is 0.061 into how much is RC? 2 kilo ohms. So how much is the gain that we are getting?
123.
123. Okay. So the gain is 123. Do you find 123? Okay, 123 is here, but okay, we have to find the gain in dB. So here see, the moment you found 123.08, you would go for this, right? Because it is there in the options. But this is not the correct answer. Why? Because we have to find the gain in dBs,
TVs.
decibels, yeah. So how do we find the gains in dB?
Ma'am, 10, 10 LN GM Y into RC.
Is it 10? Okay, so there are two things, okay? 10 ln AV or 10 log AV, 10 20 log AV, 20 log 20 ln AV. So out of these four, which one is correct? A, B, C, D. Out of these four, which one is correct? And which one will be used here? Like, what is the appropriate one?
Now I think option D is correct.
Option D is correct. Acha, why do you think option D is correct? So what is so you are saying ln AV, earlier you were saying 10, now you are saying 20, right? So there might be some reason, no, like why we are not
Actually,
going for
ma'am, I was saying AV square.
AV square. Oh, okay. ठीक फिर तो 20 होता है. But now the question is Will it be ln or will it be log?
Then ln only.
No, actually it's log. So the idea behind dB is, let's say if it is a power gain, okay? If it is a power gain and you want to find it in dBs, then we go for 10 log base 10, okay? Log base 10 P out by P in, which is in terms of, let's say, current if we write, or voltage if will be right, it will be I out square by I in square, right? With some factor of resistances, है ना?
Yes, ma'am.
So that is the idea. Now when we say in voltage gain, dB is 20 log base 10 V out by Vn. Okay, so this is very important to know. First of all, it's 20 log, and secondly, this log is log base 10, not log base 20. Okay, so
Okay.
whenever we are finding gains in dB, it's log base 10, not log base e. Okay, so yeah, this is correct. All four are wrong. So yeah, so if we want to go for the gain in dB, so it will be 20 log 10 123. So how much is it that you are getting? How many dBs?
Ma'am, 41.79.
41.79 dBs. Okay, let's see. Do you have 41.79? So 41.8. So this is the correct option. This is clear? So that is
Yes, ma'am.
very, you have to be very careful while reading, okay? So if it was not written in dBs, if it's just mentioned to find you voltage gain, then you would have reported 123.1 as your answer. But if it is mentioned in dBs, so you have to write, go for 41.8. So you need to be very calm and just go through question once before going for the answer. क्योंकि the person or the faculties who are forming the problems, they also know where students go wrong with, right? So here also you can see both the options were given. So the moment you see the answer 123.1, you will be like, I got the answer, and you go ahead with that. But the actual answer is 41.8. So you need to be very careful about it. Okay. So this is clear, right? So let's move on to the next problem. So in this same, yeah, in this same circuit, find the value of signal capacitance, this C1, such that the lower cutoff frequency of the amplifier is 200 radians per second. So 200 radians per second matlab, what is this actually? This is omega.
Omega.
Omega is given to you. So when you have to find C1, so how do you write omega? Omega is actually written as 1 by RC or 1 by CR. Okay? So now which R and which C we will consider to write this omega? So
Ma'am, input RB.
yes, so it will be C1 and RB. So here we have to find C1, so we will simply write 1 by omega into RB. है ना?
Yes, ma'am.
So C1, and let's break it, yeah, so we can write it as 200 radians per second into RB was 470 kilo ohms, right? Yeah, so how much is the capacitance that we are getting? RB, yes, it is 470. How much is the capacitance that we are getting? Okay. There is another question. Yeah, go ahead. What is the value that you are getting? C1? 0
0.0106
point
microfarad.
0 point
0.1 0.0106
0.010
microfarad.
microfarads. Okay, do you find any option close to your answer?
No.
No, right? And one more thing. So here we are saying that for this particular frequency, what is frequency or omega, we'll write it as 1 upon RC, right? This C is the input capacitance. Then this R will also be input resistance, right?
Yes, ma'am.
So is Rn only Rp over here in case of a BJT? Will this R be only equal to Rp?
And do we
R by with
consider alpha?
Yes, we need to consider Rpi. So how your small signal circuit will look like from your base, let this be emitter terminal, and this side we'll have a collector terminal, right? So here we'll have a Rpi also, right? Which is between base and emitter, considering emitter to ground. So when we are saying this resistance is Rn, it should actually be Rb parallel to Rn, right? Or Rb parallel to Rpi, correct?
yes, ma'am.
So yeah, so omega is actually, this is wrong, omega is actually C1 into Rn, where Rn is equal to Rb parallel Rpi. Is this clear?
Yes,
Is
ma'am.
this argument clear? Okay, so now we need to find Rpi. So what is the value of Rpi? How do we find Rpi?
Ma'am, beta into Vt upon Ic.
Beta into Vt upon Ic, which is beta by Gm, right?
Yes, ma'am.
Beta we know 80. Gm, how much was the Gm in the previous question? We just calculated Gm, right? 120, no, 0.061 Siemens. So it's 80 by 0.061. So how much is the Rpi that we are getting?
Ma'am, 1311.47
1311.47. What is the unit? Ohms, kilo ohms, mega ohms,
ohms.
ohms. So that means Rpi is 1.3 kilo ohms, right?
Yes, ma'am.
So how much will be Rn? 470 kilo parallel to 1.3 kilo ohms. How much we will get Rn? Rn will be close to 1.3 kilo ohms, right?
Ma'am, 1.29.
1.29. See, the moment you calculated, then also you got it to be 1.29 kilo ohms, and we can simply write it as 1.3 kilo ohms, right? And how could I say it will be 1.3 kilo ohms? Because whenever two things are in parallel, the smaller one becomes the prominent one. Smaller value becomes the prominent value. And here 1.3 is much smaller than 470 kilo ohms. So that's why I simply said it will be 1.3 kilo ohms. Okay. So
Yes, ma'am.
yeah, now we got Rn. So how much will be our C1? C1 will be 1 by 200 into 1.3 kilo ohms. Now what is the C1 that you are getting?
Ma'am, 3.84 micro.
3.84 microfarads. So let's see. So closer one is 3.85. So this is the correct answer. Clear? So see, why we made this first mistake when what we did, we didn't consider Rn but we went ahead with Rb. क्यों? क्योंकि from here we cannot actually see the R pi coming into picture. क्यों? R pi is inside this transistor, right? Circuit में when we were looking at the circuit, we could only see Rb from the outside, but R pi is internal to the transistor. So there was this need to consider the R pi. Okay? So that is the mistake that we did in the first method. Is it clear?
Yes, ma'am.
So yeah, see, that's why I also go for wrong methods, because generally how we think, we start from something wrong, okay? Then we find out, okay, this is wrong. Where we went wrong, we recalculate it and do it again. So what happens? You will never make that mistake again, because you'll remember this thing, okay, here we did the same mistake we repeated earlier and we got the answers wrong. Now we need to proceed the other way. This will stay in our mind. That's why it is very important for you to make mistakes and learn out from the mistakes. Okay? So is this clear to everyone what we did here? Why we
Yes, ma'am.
consider Rn, is this clear to everyone? And Rn is not Rb, but it is actually Rb parallel to R pi. Okay? Alright. So here, since we calculated Rn, so let's calculate R out also. Hai? So we have VA, right? And we also have IC. So what is the value of R naught? How do we write R naught?
VA by IC.
VA by IC. So VA is 120, IC is 1.6 milli, 1.6 milliohms, right? Sorry, 1.6 milliamps. So how much is R naught that we are getting?
75 kilo ohms.
75 kilo ohms. But when you look at this circuit, I'll place this circuit over here. Yeah. So, okay. So now when I say R out, what will be my R out? Will it be R naught?
Ma'am, R naught parallel with RC.
Yes, R naught parallel with RC. So R naught is intrinsic to this transistor, whereas R out is the output resistance seen from outside of the circuit, okay, from this output terminal. So here it is very necessary to differentiate between the two. This is intrinsic to the transistor, R naught, and this is the output resistance of the whole circuit. Clear? Okay. So what will be the R out? It is 75 kilo ohms parallel to, how much was RC? It was 2 kilo ohms, right? So yes, what will be the R out?
1.94 kilo ohms.
1.94 kilo ohms, or if we round it off, it will be 2 kilo ohms, right?
Yes, ma'am.
So here also you can see the difference. So here also we are getting the impact because of the smaller one. So when we are considering parallel connection, it is very important to look at what is the smaller value, and when we are going for a series connection, series resistance, then we need to consider the effect of the largest resistance. Okay, this is the condition we need to follow for resistances. So when two resistances are in series, R, where R is much greater than R. So R net will be equal to capital R, right? But when there are two R's which are in parallel, for the same condition, R net will be equal to small r. Now, if this is the condition for resistances, what about capacitances?
Just opposite.
Just opposite, because in series, when capacitances are there in series, so their effective is 1 by C net is equal to 1 by C1 plus 1 by C2, right? So it will be simply opposite. So this is something we can keep in mind, and just in case if we are in a hurry, we can make the assumption, because here you can see that it was closely equal to 2, right? But for that, the values need to be far apart. If it was, let's say, 10 kilo ohms parallel 2 kilo ohms, I would not have said R net or R out will be 2 kilo ohms. At that point of time, my answer would be wrong. But let's say if it is like 1000 kilo ohms parallel 2 kilo ohms, I can simply say that my R out would be 2 kilo ohms. So that relativity is very important. Is this clear what I am trying to say?
Yes, ma'am.
Okay. So yeah, we have found R out to be 2 kilo ohms and Rn also to be, how much was the Rn? 1.3 kilo ohms. Okay. So yeah, coming to the next problem. Actually, there was this problem based on R out and R in. So in place of that question, the same question got pasted twice. But we already solved it, so you know how to solve it. Yeah. Now coming to the fourth question. So here we have to find the maximum output swing without a significant distortion from sinusoidal input for the circuit shown in figure 4.1. So in this particular circuit, we have to find output swing. So what do we understand by output swing? What do you basically understand by swing? Whether it be an input swing, output swing, what is swing in terms of circuits?
Ma'am, it goes to a maximum value, then comes back to a minimum value, and it just repeats like that. It's a swing.
So if there is a sinusoid, so it's maximum minus minimum, right?
Mm.
So if let's say this is a mean value, then this minus this will give you the swing. So Vmax, Vmin. Swing will be Vmax minus Vmin, right? So what is output swing then?
At the output side, what's the maximum output voltage minus minimum voltage?
Yeah, what is the maximum and what is the minimum that we can get? So why are we concerned about the swing? Like, why do we even need to consider this swing? Let's say output swing or input swing in our circuits.
Ma'am, at below certain point, the transistor won't work properly. It will give some kind of distortion. So we
Mm-hmm.
need to consider that also to create some reliable
So,
circuit out.
what do you mean by distortion? Like, if you are a circuits engineer, what is distortion do you mean?
Distortion means if it is supposed to go you have represented a sinusoidal signal here.
Hmm.
So on the negative side, it is going like a circular way. But because if it is distorted, then it will be chipped at some value, and the lower portion will get cut out.
Okay. So, first of all, first things first, swing. So, where does this concept of swing comes from? So, we all know that we want a linear amplifier, right? Whether it is made up of a transistor or a MOSFET, we want a linear amplifier. What do you mean by linear amplifier? When we say we want to design a linear amplifier or we want to use our amplifier in a linear mode, what do we mean by that? What is linear amplification?
Linear will mean that at every point of time we are getting the same gain. It shouldn't happen that at one point we are getting more gain as compared to others. So then the signal will get. It's not a proper reproduction of the input.
Hmm.
It is like distorted or not a reliable output from
Yes,
inputs.
yes. So what we mean is, let's say I'm giving an input of 1 kilohertz. So my output should be gain times of 1 kilohertz signal only. I should not see any other harmonics. Okay, if we go for a very technical term, then linear amplification means you should not see any other harmonics or any other frequencies other than your input frequencies. Clear? And when even we say that our output is being clipped or it is being flattened at the top, what it actually means is when we say, have you ever heard of Fourier series, Fourier transform, frequency
Yes,
response analysis? Yeah. So when we do the Fourier analysis for sine wave, it's actually a single frequency, right? But when we go for a square wave and do its Fourier series, it's actually multiple sine waves. Okay, where each sine wave corresponds to one frequency. Clear? So when it gets clipped, basically that means at that point it becomes closer to a square wave, right? Now it's not a sine wave. It's distorted means it's becoming close to square wave. The more you clip it, the more it becomes closer to a square wave. You can visualize it, right? So let's say if this is my sine wave, and if I clip it over here, I'll see, okay, there is a small distortion. But if let's say I clip it over here, it is very close to a sine wave, right? Square wave, right? So the more you clip it, the more it becomes closer to a sine wave, a square wave. That means the more number of harmonics are being added. Because the moment you send this clipped signal and you see its frequency response, you'll find out that along with this, let's say 1 kilohertz signal, 1 kilohertz peak, you will see other peaks also, which will be smaller in magnitude, but those frequencies will start appearing. So that is what you don't want. So if you want to say it in a very technical term, what you can say is that a linear amplifier means that my input frequency should be replicated to my output frequency with a certain amount of gain. And as you said, the gain should be constant for each and every part, and I should not see any other frequencies other than my input frequency. Then I'll say that my circuit is a linear circuit. Okay? So these things that we see, okay, the output being clipped and all, it is something which we observe. But what is the physics behind it is actually the introduction of harmonics. That should not happen. Is this clear? Any doubts? Or you didn't understand anything? Please let me know.
ma'am, can you please again
Yeah.
tell?
So see, what we are discussing is a linear amplifier, okay? So linear amplifier, as I guess Jyoti said, that an amplifier for this particular sine wave, for each and every point, it should give me a gain of G. So it should replicate G times that input, okay, in my output. That is what it should do. And what I am saying is, it will definitely give you G times the input, but its frequency, input frequency, should not change in the output. So let's say if you give a 1 kilohertz signal to your input, your output should also be a 1 kilohertz signal. Then you will say your circuit or your amplifier is a linear amplifier. Okay, or to be to express it in a more technical term, how we will say, we'll say it like your amplifier should not add any harmonics to your output. There should not be any harmonics present in your output. Then your amplifier is a linear amplifier. Okay, to make it even more technical. And if we talk about, okay, how things will be visible to us when we are looking at the outputs, so as we mentioned earlier, your output starts to get clipped. Okay, so the sign doesn't appear as a sign, but it starts getting clipped from the top. Then you realize, okay, like harmonics are being added to your system. So that's why now your sign is not being translated as a sign, but it has been distorted. This is how you look into it visually. But what happens in the background, or what technically happens, is actually harmonics get added to your input signal. Is this clear?
Yes, ma'am.
Yeah. So the swing comes from that linearity. So what is the maximum input from peak to peak that you can apply to get a maximum output peak to peak signal which is not distorted? That is, your amplifier behaves as a linear amplifier. That range we want, and that is what is called as a swing. Clear? So yeah, now let's solve this problem. So for this particular circuit, what we have to do is we have to find the swing. Now how do we find the output swing? So let's say if this is E, this is C, and this is B. So the moment I find VC, let's say this is VDD, this is ground. Okay, and I have my, so in this VDD to ground, how much is the maximum swing that we can get? It will be VDD to ground, right? Peak to peak you can have VDD to ground.
Yes, ma'am.
When you will get VDD to ground? When your output, this is V out, right? So what is the condition when you get your swing to be VDD to ground? When there is no constraint on anything, there is no drop across any resistor or any transistor, and your V out is at VDD by 2, right? Because sine wave is a symmetric wave, so the amount it goes above the mean value, it will come below the mean value with the same amount, right? So this is VDD by 2, and this will also be VDD by 2. At that point of time, you will have a total swing of VDD, right?
Yes, ma'am.
But now, this is one condition. Now let's say your V out is placed somewhere over here. This is V out dash, with this value being VDD by 4. So the remaining will be 3 VDD by 4, right? So now if this is the case, then what will be the swing that we will get? For this V out dash, what will be the swing that we will get? Is this concept of swing clear? अभी तक जो डिस्कस किया था, did you understand how we reached, like why I chose this VDD by 2? Is this clear?
Ma'am, PDD by 2 is clear.
VDD by 2 is clear. So if that is clear, now what about V out dash के केस में क्या होगा? What will be the peak to peak swing that you will see?
VDD by 4.
VDD peak to peak कितना होगा? See यहाँ पे when your output is placed at VDD by 2, your swing was of VDD, right? Top to bottom, है ना?
Yes, ma'am.
Now your output is placed at V out dash. So at this point, which is actually VDD by 4 away from your VDD and 3 VDD by 4 away from your ground. So इस case में what will be your peak to peak swing?
I'm not sure, but VDD by 2.
And yeah, one more thing, that sine is always a symmetric wave. So the amount it goes above the mean value, it will come down with the same mean value, right? So yeah,
Yes,
the
ma'am.
answer is VDD by 2. क्यों? क्योंकि यहाँ पे ये VDD by 4 से ऊपर जा नहीं सकता है, राइट? उसके ऊपर there is no scope. तो ये maximum VDD by 4 travel करेगा. So it will come down by the same amount VDD by 4, right? And again it goes up by VDD by 4 and comes down by VDD by 4. So if you look at this peak to peak value, it's actually VDD by 2. And this amount is being wasted. We are not using this range, right?
Yes, ma'am.
So इस एग्जाम्पल से क्या समझ में आता है? एंड सी इफ दिस इज आउटपुट, तो तुम्हारा इनपुट किस पे डिपेंड करेगा कि तुम्हारा आउटपुट स्विंग कितना है. क्यों? क्योंकि इनपुट इज वी आउट बाई जी, राइट? वी आउट बाई गेन, है ना? तो तुम्हारा आउटपुट स्विंग कितना है उससे डिपेंड करेगा कि तुम्हारा इनपुट तुम कितना अप्लाई कर सकते हो, राइट? सो व्हाट कैन यू इन्फर फ्रॉम दिस? What is the learning that you will get out of this?
Ma'am, that for distortion-free amplification, we can only have a certain amount of swing in the input.
Yeah, that is true. But what can you say about your output point? Like, where should you bias output? What can you say about that?
Ma'am, one thing I need to ask.
Yeah.
Ma'am, in that second one, second wave you have represented using blue.
Yes, yes.
Ma'am, is the average VDD by 2 or 4 there? Ma'am, can you please explain that point?
So yeah, here it is actually it's placed at 3 VDD by 4. So this point from VDD, it's VDD by 4 away, and from ground it's 3 VDD by 4 away. So if I write it down, this value is actually placed at 3 VDD by 4. 3 VDD by 4 पे होगा तभी ऊपर से you will only have VDD by 4, right? Or from bottom you will see that 3 VDD by 4. Is this clear? Any doubt?
Ma'am, the average should be taken on max minus minimum divided by 2 we are taking, right?
Max minus min divided by 2 we are taking for what?
To find out the swing.
No, so swing, I am saying the swing is actually max minus min.
Correct.
V max minus V min, okay?
Correct.
So this will give you swing peak to peak.
Correct.
Peak to peak. So that means from where your sine का maximum minus minimum, वो कितना है range? Earlier when your V out was biased at VDD by 2, there you could find a complete swing of VDD because VDD minus 0, ground is 0. So you were seeing your swing to be VDD peak to peak.
Correct, correct.
है ना?
Peak to peak is VDD, correct.
Yes, peak to peak is VDD. Now what I did, I have shifted my bias point and my V out is now biased at 3 VDD by 4. Okay. So at this point, how will my sine look like? See, sine is always a symmetric wave, right? We'll consider it as a symmetric wave and we don't want any distortion. That is what we discussed, right? We want linear amplification. So
Correct.
there should not be any distortion. So my sine should appear as a complete sine. So now in that given range where my output is biased at 3 VDD by 4, let me draw it clearly again so it's clear. So this is 3 VDD by 4 and this is ground, which is 0 volts, right? Now in this particular situation, how much will be the swing, that is peak to peak, that I will get from this type of arrangement? Clear?
Yes, ma'am. Clear.
So how much is the peak to peak that we will get? So now when this is 3 VDD by 4, that means this value is actually VDD by 4 and this is equal to 3 VDD by 4, right? So in this I have to fit a symmetric sine wave. So how will my symmetric sine wave look like in this arrangement? How will my symmetric sine wave look like?
Yes, ma'am. I got it now.
You
Yeah.
got it? So it will start from this mean value. It will go till VDD, which is value VDD by 4, and then it will again come down and it will travel till this. So this VDD by 4, that is actually VDD by 2. So now when I look at it, so what is the swing peak to peak that I am seeing? It's actually VDD minus VDD by 2, that is VDD by 2, right? Clear, no? So this is what I was discussing. So now, yeah, my question was, so what is it that you can infer from this information that we discussed till now? What I mean to say is कि क्या फ़र्क पड़ेगा कि मेरा bias point कहाँ पे है? Bias point means my V out. V out is my bias point, right? It depends on how we are arranging our resistors and how much is the currents that we are providing. All these are something which comes out from what we are applying to the circuit. Like ये मैं resistor change कर दूँ, मेरा output change हो जाएगा? Yes or no?
Sorry ma'am, आपने अभी क्या बोला?
If I change this resistor to some other value, will my output bias change or not?
Yes ma'am, it will
Yes,
change.
it will change. So this is biasing point, right? V out, and it's in our hand. We can modulate it. So we should always try. So here what we are actually doing is हमें एक circuit दिया गया है and we are analyzing the circuit, ठीक है? But what circuit engineers actually do is they design the circuits. ये सर्किट जो आपको दिया गया है ये कभी किसी ने डिज़ाइन किया होगा और आपको भी कभी कोई सर्किट डिज़ाइन करने दिया जाएगा. उस समय आपके हाथ में क्या होगा कि लेट्स से यू हैव करंट, ठीक है? You have this much amount of current that you can supply to your circuit. You have the power dissipation which should not go beyond this. You have gain as your parameter. Okay? You have bandwidth as your parameter. With all these parameters, you have to design your own circuit. Okay? And in that circuit, you need to see, okay, how much is the swing that you are getting. The more the output swing, the more the values or the more the range of inputs that you can provide to your circuit. ये समझ में आ रहा है? Is this clear what I am saying? See,
Yes ma'am.
output swing जितना ज़्यादा होगा, output swing divided by gain will give you input swing. ठीक है? So जितना maximum output swing है, तो उतना maximum तुम्हारा output जा सकता है. तो उस पर डिपेंड करेगा कि तुम मैक्सिमम इनपुट कितना दे सकते हो अपने सर्किट को. तो जितना ज़्यादा स्विंग होगा उतना ज़्यादा तुम इनपुट प्रोवाइड कर सकते हो, उतने ज़्यादा लेवल ऑफ इनपुट्स तुम प्रोवाइड कर सकते हो. तुम्हारा इनपुट मैक्सिमम भी बढ़ जाएगा. So while designing a circuit, you should always keep this in mind that your swing should be as maximum as possible. ठीक है, तो कभी भी जब हम सर्किट डिज़ाइन करते हैं, हमें जो स्पेसिफाई किया जाता है कि हमें गेन इतना चाहिए, हमारा पावर डिसिपेशन इतना होना चाहिए, हमारा करंट इतना होना चाहिए, हमारा सर्किट जो है इतने से इतने फ्रीक्वेंसी में काम करना चाहिए. Along with these parameters, another major things that is not always mentioned, but it is something which you need to keep in mind, that is output swing. तुम्हारा output swing कितना आ रहा है, and the best optimized circuit is which specifies all the given parameters. Along with that, it gives you one of the best output swings possible. ठीक है, तो आउटपुट स्विंग इसलिए बहुत इम्पॉर्टेंट है क्योंकि यहाँ पे जब हम सर्किट सॉल्व कर रहे हैं तो उसका इम्पोर्टेंस उतना नहीं समझ में आता है, लेकिन जब आप एक सर्किट डिज़ाइन करते हैं देन यू एक्चुअली रियलाइज द इम्पोर्टेंस ऑफ दैट आउटपुट स्विंग. ओके, तो हमारा और हम इसलिए कभी भी बायस पॉइंट, और ये जो वी आउट पॉइंट है इसको हम बायस पॉइंट बोलते हैं, राइट. और ये हम सेट कर सकते हैं डिपेंडिंग ऑन द रेजिस्टेंस वैल्यूज, ऑन द करंट्स दैट वी आर यूजिंग, है ना. तो वी ऑलवेज ट्राई टू फिक्स दिस वी आउट सच दैट वी गेट द मैक्सिमम स्विंग. और इस एग्जाम्पल में, द एग्जाम्पल दैट वी वर लुकिंग, what we said कि for the maximum output swing we need to bias it at VDD/2. ये हर केस में पॉसिबल नहीं हो सकता. यू कैन नेवर से कि यू विल बायस इट एट VDD/2 एंड यू विल गेट अ मैक्सिमम स्विंग. नो, दैट्स नॉट पॉसिबल, बिकॉज देयर माइट बी अ पॉसिबिलिटी, जैसे मैंने यहाँ पे बोला कि रजिस्टर के मतलब इस ट्रांजिस्टर के अक्रॉस कोई ड्रॉप नहीं हो रहा है, लेकिन ऐसा नहीं है ना, इसके अक्रॉस भी ड्रॉप होगा, तो दैट वैल्यू विल बी रिमूव्ड, राइट. सो वी नीड टू कंसिडर दैट ऑल्सो. तो अभी जब ये प्रॉब्लम सॉल्व करेंगे सो यू विल इवन बी एबल टू ऑब्जर्व इट वेरी क्लियरली लाइक व्हाट आई एम ट्राइंग टू से. ठीक है, अभी तक ये समझ में आए, द स्विंग, इट्स इम्पॉर्टेंस, लीनियर एम्प्लीफिकेशन, इतनी चीज़ें समझ में आई बेसिक्स में. एनी डाउट्स?
All clear.
ऑल क्लियर नो, समझ में आया ना.
Yes, ma'am.
चलो अब इसके बाद नाउ लेट्स मूव ऑन टू द एक्चुअल क्वेश्चन दैट वी हैव. ओके, so in this particular circuit you have to find the maximum output signal swing without significant distortion for the input signal being provided to the circuit. तो इसमें to find out the maximum swing, what is very important, you need to find out this V out कि कितना है तुम्हारा पॉइंट, कहाँ पे बायस्ड है ना. So let's find out this V out. What is this V out? It is actually VC, right? Or how will you find VC? It is ICRC, है ना. So
Yes, ma'am.
the moment I find IC and I multiply it with RC, I'll get my V out. So how much is my IC? 1.6 milliamperes, and RC was 2 kilo ohms if I'm not wrong, right? So VC कितना होगा? 3.2 volts, है ना.
Yes, ma'am.
3.2 volts होगा. ये तो आ रहा है यहाँ से यहाँ का वैल्यू. अब ऊपर का भी एक बार देख लेते हैं. ये तुम्हारा कैसा है, जैसे this is between VDD and ground, right? So here you have found certain point 3.2 volts which is between like V out and ground. Now अगर suppose तुम्हारा ये VDD और ground V out के बीच में भी there is certain point above which you cannot go, and this is less than 3.2, so you will select the one which is smaller. ठीक है, now let's say this is 3.2 volts, और यहाँ पे because of let's say certain conditions या something you got this value to be 1.5 volts for example. Okay, so what will be your swing? You cannot go beyond this point. This is not possible. This is 1.5 volts that span from V out to this point. and from V out to ground you have 3.2 volts. So how much is your output swing that you will get in this example?
3 volts.
Yes, 3 volts. तो it is like 1.5. तो जो मिनिमम है उसका ट्वाइस. ये क्लियर है ना? सो
Yes, sir.
हाँ, सो नाउ लेट्स सी अब क्या होगा. सो ओके, हियर वी हैव फाउंड आउट कि VC टू ग्राउंड हमारे पास 3.2 वोल्ट्स है. नाउ व्हाट अबाउट दिस VDD टू VC, यहाँ का क्या सीन है ना? सो VDD टू VC के बीच में ये क्या आ रहा है? व्हाट इज़ दिस एक्चुअली? VDD टू VC की जो हम बात कर रहे हैं, इट इज़ एक्चुअली VCE, राइट? VDD तुम्हारा VE है और VC तुम्हारा VC है. तो अगर तुम ऐसे देखोगे सो इट्स एक्चुअली VEC, क्योंकि ये PNP ट्रांजिस्टर है तो इट इज़ VEC. सो हाउ मच कैन योर VEC go? So when we started the question, in the very first question there were many specifications given, right? उसमें एक specification ये भी था, VC sat. What does this mean? What does VC sat means? Yes, what do you understand by VC sat?
Ma'am, to keep it in the linear region, at just this point, if we go beyond that point, it will switch to saturation region.
Yes. So for a BJT to work as an amplifier, it needs to be in an active region, okay, active mode of operation. So the moment your VEC goes less than 0.2, your transistor will switch to saturation and you will not see any amplification happening. So your circuit will not behave as an amplifier. Clear? So this is something we need to keep in mind. So यहाँ पे VC sat is given 0.2 volts. So your VEC should be greater than 0.2 volts to keep it in active region. Clear? So if we have to keep it more than 0.2 volts, that means your VC or your Vout point should be less than 9.8 volts. Is this clear?
Yes, ma'am.
9.8 is clear? क्योंकि the moment your VC goes beyond 9.8, what will happen? Your transistor will move to saturation region and it will not amplify anymore. So that's why this 9.8 came. So now इसके ऊपर क्या हो रहा है कि this is your Vout point and Vout का from Vout to ground you have 3.2 volts and the maximum this Vout can go till 9.8 volts. Is this clear? So now if this is the situation, so what will be my output swing? Output swing will be actually 2 times the minimum of 3.2 or 9.8. 9.8 नहीं, actually ये कितना होगा? 3.2 minus 9.8, it's 6.6, right? Yeah. So it will be minimum of 3.2 or 6.6, है ना? यहाँ से यहाँ तक का it is 6.6, right? If this is 9.8, because this is at 3.2. So swing क्या होगा? जो minimum value है उसका double. So that's why your output swing will be 6.4. Is this clear? This is peak
Yes,
to
ma'am.
peak. This is peak to peak. It is very important. और जनरली बहुत दिक्कत होती है स्विंग को समझने में. स्विंग इज़ नॉट वेरी इजी. इट्स अ लिटिल ट्रिकी, नॉट वेरी ट्रिकी but a little tricky. So if you feel any confusion, any doubt, feel free to ask. किसी को भी कोई भी डाउट हो, किसी को नहीं समझ में आया हो, फील फ्री टू आस्क, आई एम हियर टू हेल्प यू ओनली.
Ma'am, this is PNB transistor,
Yes.
and NPN transistor we consider the lower limit. I mean, from 0 to point 2, that portion, just like you considered on the upper side, from 10 to 9.8, you considered
हाँ हाँ.
should not go beyond that point to
Yes,
allow
yes.
ensure proper working. So in NPN transistor, we are considering on the lower side, right?
हाँ, NPN ट्रांजिस्टर में उल्टा हो जाएगा ना, तुम्हारा एमिटर नीचे आ जाएगा, कलेक्टर रजिस्टर ऊपर आएगा और यहाँ पे तुम्हारा वी आउट रहेगा. तो यहाँ पे अब ये तुम्हारा ग्राउंड है, यहाँ तुम्हारा VDD है, एंड दिस इज़ नाउ CB एंड E. सो यू हैव टू कंसिडर दिस. और अगर मान लो वहाँ पे भी लेट्स से 0.2 है, तो हम लोग वहाँ पे ये लेके चलेंगे, तो वहाँ पे ग्राउंड नहीं आएगा. जैसे यहाँ पे ग्राउंड है ना, उस केस में क्या हो जाएगा, इट विल बी स्टार्टिंग फ्रॉम VDD बट इट विल एंड एट 0.2 वोल्ट्स. वहाँ तुम्हारा ग्राउंड तक जाने का लिमिट नहीं रहेगा. सो योर स्विंग विल बी लिमिटेड फ्रॉम VDD टू 0.2. ये
Yes.
चेंज होगा PMOS होने से, मतलब PNP होने से, सॉरी NPN होने से, बिकॉज हियर इट इज़ PNP. ये क्लियर है?
Correct. Yes, ma'am.
ठीक है ना? और बाकी चीज़ें समझ में आई ना?
Yes, ma'am.
ओके. सो आई होप स्विंग इज़ क्लियर. वी हैव डिस्कस सो मच. सो कहीं भी कुछ भी डाउट हो स्विंग में, सी स्विंग इज़ नॉट वेरी ईजी, आई एग्री. That's why please ask whatever you feel you are not comfortable with, just please feel free to ask.
Ma'am, can I ask, ma'am,
Yeah.
if you want to practice more questions, which book should we follow for this?
Uh, so there is no book mentioned in the course plan
Okay.
and for the circuits.
No, ma'am. Just like you are taking some examples from, I
Yeah.
think one of the books. Can you just give me that book's name?
Actually, these are few previous year problems that we are picking and solving. But if you want to know like books, so maybe I can tell like there is a book on Razavi.
Yeah, yes, ma'am.
In
Yes, sir.
Razavi, there are these problems based on small signal biasing, all these problems with and without source resistor, emitter resistor, all these type of problems you can find in Razavi. So yeah, you can practice problems from there. And if you want MOS based more problems, so I have taught MOS based problems last semester. So they're in my same YouTube channel. So from there you'll find more problems, but they are MOSFET based. BJT based nahi hai usme. They are only based on MOSFETs. But you can find enough problems. So that was also for 12 weeks. It was for 12 weeks, so you'll have at least 12 set of problems based on MOSFETs. So in the same channel.
Okay.
It's like last semester's video recording is there. So there you can find.
Ma'am, under the same subject name?
Yes, same subject name. And actually the moment you go to my channel, so I have started teaching this from last semester only. So दो playlist होगा. This is Jan 23 वाला, and the other playlist is that last semester's one. So you can go and refer to it. उसमें MOSFET based मिल जाएगा. And you can refer to Razavi. Like Razavi में there are solved problems as well as a lot of exercise problems. They are based on these small signal models, everything. So Razavi,
Is
yeah.
there only one book of Razavi or multiple editions? I'm just looking.
Basic, I guess one book is there which is for basic circuits. And if you want to go for advanced, so there is like analog CMOS IC design एक book है. उसमें you will find advanced circuits. Advanced circuits मतलब जैसे current mirror circuits, or you will find differential amplifier based circuits, OAT based circuits. These are advanced level. यहाँ पे you are going for one transistor, like धीरे धीरे you will see two transistors coming into picture. Then the number of transistors increase and the circuits become more and more complex. So yeah, So for more advanced problems, you can go for analog CMOS IC design. I guess that is also by Vazavi, if I'm not wrong. And for basic problems like for one MOSFET or two MOSFET, one BJT, two BJT, you can go for Vazavi. Vazavi में you can get basic problems.
Okay, ma'am.
Yeah, you can refer to that. और ज़्यादा अगर ऐसे सॉल्व प्रॉब्लम्स का वीडियो चाहिए तो आई हैव माई वीडियोज़ ऑल्सो, सो यू कैन गो थ्रू दैम एज वेल. तो सेम चैनल यू नो राइट.
Yeah, yes, ma'am.
सो उसी चैनल में देयर इज दिस प्ले लिस्ट, तो उसमें आपको मिल जाएगा.
Yes, ma'am. Thank you, ma'am.
Okay, yeah. So hope this is clear how we found out the output swing. No doubts, right? I hope there are no doubts. If there are doubts, please feel free to ask. See, this is something to help you people. So whatever doubts you have, please feel free to ask. Now see, so अब क्या आया? Maximum input signal swing. So the moment you have found output signal swing, so how will you find input swing? How are output and input related?
Divided by gain.
Yes.
Output.
So input swing is output swing by gain. We found out the gain, right? How much was the gain? Gain निकाला था ना हमने. Oh, this is the same problem going on. So it was 123.1, I guess, है ना?
Yes, sir.
Yeah. So we'll simply divide it by 123.1. So कितना आ जाएगा? 6.4, 123.1. How much is this?
And 0.05.
0.05. What will be the unit?
Millivolts only.
What is the unit? 0.05 क्या होगा unit?
Volts.
Volt peak to peak. So ये आएगा तुम्हारा around 50 millivolts peak to peak. So this is 52 is the answer. Clear? Now here you can observe, right? अगर यही मेरा output swing मान लो 10 होता तो मेरा input maximum जो आ सकता था, maximum input swing, वो भी बढ़ जाता ना. तो मैं ज़्यादा amount of input I would have been able to amplify, right? Yes, Vasanti. Do you have any doubt? You can unmute and ask. So can you observe the importance? Can you teach week 6? But Vasanti, we are at week 4. So we won't be able to skip the problems, right? Yeah, so that's why we are going week by week. So last year it was like last week it was week 3, so this week it is week 4. Yeah. And if you want to solve week 6, so maybe you can build upon the basics from here and you can solve the advanced problems. That will also do. Yeah. So now here you can clearly observe, right, the importance of output swing. Like why output swing is that important. ये clear है ना? And एक और चीज़ देख सकते हो, that your input swing is inversely proportional to gain. So the more the gain of your circuit, the lesser input you can provide to maintain the swing. ये clear है?
Yes, sir.
है ना? I hope all these things are clear to you. So yeah, without any further ado, let's move on. So now in this question, so there is this another circuit, a beautiful circuit. So what is different from other circuits over here? क्या different है इस circuit में? What is it that makes it look very different from previous circuit? Yes. What is different over here?
Biasing arrangement is different.
Biasing arrangement is different. So we have for like base, we have R1 and R2, it is series resistance or resistance divider. What else is different?
RE is present.
Yes, RE is present. What else?
CE is also
C is
present.
also present, the switch is present. So now you can see from the previous circuit, this circuit is even more complex, right? This is clear, no?
Yes, ma'am.
This is clear, yeah. And how does its small signal will look like? So it will be somewhat like R1, R2. I'll make it quickly so that we'll have time to discuss other things. R pi, RE. VBE, what else? R not parallel, RC. This is VC, VB, VE. This is how your circuit will look like, है ना?
Yes, ma'am.
इसमें CE भी डाल देते हैं with the switch. This is how your small signal will look like. इसमें कोई डाउट है? किसी को लग रहा है गलत है, सही है, एनीथिंग? ये ठीक है?
सही है।
हाँ सही है ना। चलो तो इसमें देखते हैं आप पूछा क्या है, हमें दिया क्या क्या है। R1 is given 40K, R2 is given 80K, RC, RE both are 3.3K, VCC is 12 volts, VEB again EB क्यों? Because it's an PNP 0.7, VEC SAT is again 0.2 volts, beta is 100, VT is 26 millivolts. Early voltage is very high, so considering VA to be very very high. So VA अगर very high होगा तो what is the significance?
We can ignore the attenuation of VC.
हाँ
Change in
अच्छा नहीं ठीक है तो
changes by
स्मॉल
VC.
स्मॉल सिग्नल में क्या इंपॉर्टेंस आता है इफ VA is much much greater or very high?
RO will be very high.
Yes, RO tends to infinity, so we ignore RO. Like यहाँ पे ओपन सर्किट हो जाएगा तो तुम्हारा R out क्या हो जाएगा इस पर्टिकुलर सर्किट के लिए, विच इज़ एक्चुअली R low पैरेलल टू RC इन जनरल. इस पर्टिकुलर सर्किट के लिए इट विल बी RC. ये क्लियर है? ये क्लियर है
Yes,
ना?
ma'am.
सो दिस इज़ व्हाट वी फिगर्ड आउट. सो यहाँ पे R नॉट पैरेलल टू RC की जगह आई कैन सिंपली राइट RC. So this is how my small signal looks like. These are the givens. Now let's find out. So find the DC voltage between emitter to collector of the BJT. हमें क्या find out करना है? VEC, this voltage. ये voltage कैसे find करेंगे? यहाँ पे अगर मैं KVL लिखूँगी तो उसमें मैं I can find out, right? If I write a KVL between VCC to ground, I can find out VCE, right? Or VEC, है ना? Yes or no?
Yes, ma'am.
So how will we write it? RE plus VEC plus ICRC. This is how it will look like, right? So इसमें now what is given to us? We want to find IC, IB. So how to find IB? How will we find IB? See, let's look at this one. VCC equal to IC plus IB RE or let's write it like VE is हमें VEB दिया है, ठीक है. It's actually VE minus VB. I want to find, let's say, VE. So it is actually VB plus VE. Sorry, VB is VE. ये clear है? And what is also VE? And this is VE, right? It is actually VCC minus IB plus IC into RE. This is also VE, है ना? So from these two, can I find my IC or IB? Yeah. So VEB is given point how much? 0.7 volts. 0.7 volts. How much is VB? How much will be VB? VB कैसे निकालेंगे? VCC into R2 upon R1 plus R2. Is this clear? So which is 12 into R2 is how much? 80 by 120. So VB is actually 8 volts. So यहाँ से your VE is actually 0.7 plus 8, that is 8.7 volts, which is also equal to 12 minus, I can write it as 101 into RE. How much was RE? 3.3 kilo into IB. I can write it like this. So from here we can find IB, right? 12 minus 8.7 by 101 into 3.3k. So how much is the IB that we are getting? Yes, what is the value of IB? How much is the IB that we are getting? Hello, are you there with me?
Yes, I'm just there.
Okay, fine.
9.9 millivolts. Milliamps.
9.9 9.9 ही आ रहा है मिली.
Oh, sorry, microamp.
See, unit check करो. How much is the unit?
High is my microamps.
Microamps. So if we substitute that IB over here, we'll find VEC, right? So VEC is 12 minus 101 into RE, that is 3.3k into 9.9 micro minus 100 into 3.3k into 9.9 micro, which is actually 12 minus 201 into 3.3k into 9.9 micro is
Ma'am,
VEC. Yes.
ma'am, is IB 9.9 because in the numerator 12 minus 8.7 is.
How much is the IB?
Ma'am,
12 min.
mine came out around 32.6 microamperes.
Yours is 32.6 microamperes.
Yes, ma'am.
Okay.
Because in the in the numerator there is 3.3. 12 minus
Yes.
8.7 divided by 3.3 and divided by 100.
100.
So it's almost like that 3.
Yeah, makes sense. So एक काम करो. You
Hmm.
two got two different answers, no? So you two, what you do, proceed both of you using your IDs and let me know what is the value of VEC, because I have the final VEC that I have calculated with me. So let's see who has got it correct. You calculate both of you using your own answers. Okay? Let's see. Both of you let me know your answers, है ना?
Yes, ma'am. I'll just do it.
5.4.
Okay, so you are getting 5.4 volts. Okay. What about you, Jyoti?
Ma'am, I'll just do it 1 minute. I'm not done yet.
Simply substitute your value over here, the expression में. Calculator में डाल के देखो. Okay, Jyoti, maybe you might have done some mistake. The answer is 5.4 volts, and yeah, it is 9.9 micro only. So this is not correct. So maybe you can look into it where it went wrong. Okay. IB is yes 9.9 microamperes. It's correct. And VEC you'll get to be 5.4 volts. Okay. Okay, we have a lot of questions to solve. Today we discussed a lot, but it's okay. Go ahead. So now let's say beta has been changed to 300. So what is the DC voltage VEC you have to again find out for the same circuit. So बीटा 300 हो जाने से क्या चेंज होगा? So yes. So in that same question, बीटा 100 की जगह बीटा को 300 करके you have to find VEC. Nothing you have to change, just beta is being changed. ये कर लोगे?
Yes, ma'am. ये तो कर लेंगे.
सेम ही है ना, कुछ नहीं करना है इसमें, बस 100 को 300 करना है, उससे वैल्यूज़ चेंज हो जाएंगी. और इसका आंसर मैं बता देती हूँ, सो यू कैन टैली. द आंसर इज दिस इज क्वेश्चन नंबर 7 में. इट्स 5.41 एंड अर्लियर दिस वाज 5.44. तो ज़्यादा डिफरेंस नहीं आया है. वो भी यू कैन सी कि क्यों डिफरेंस नहीं आया है, कहाँ क्या ऐसे चेंज हुआ है, क्योंकि 300 इज़ अ बिग वैल्यू राइट. 200 का डिफरेंस है, लेकिन तुम्हारे आउटपुट में तो उतना चेंज नहीं आया. VEC में क्यों नहीं आया? वी कैन एक्सप्लोर दैट, है ना. सो ये कर लोगे ना, सॉल्व करना है सिंपली. ऊपर में 100 रखा था उसकी जगह 300 रखना है. So let's move on to the next problem. So now in this what you have to do is find the ratio of small signal voltage gain of the amplifier with and without the bypass capacitor. So what are the things that change when the capacitor is present and when the capacitor is absent? गेन पे क्या फ़र्क पड़ेगा और उसके साथ साथ what will the ratio turn out to be? So let me bring that small signal circuit which we drew. This is something which will actually come into play over here. So ये तुम्हारा सर्किट है ना. तो विच बाईपास कैपेसिटर की हम बात कर रहे हैं सी की. तो सी ई में लेट्स से इफ दिस इज शॉर्टेड, लाइक इफ दिस इज प्रेजेंट एंड दिस इज शॉर्टेड, सो सोल्यूशन में देयर विल बी टू पार्ट्स विथ सी ई. इफ सी ई इज प्रेजेंट, सो स्मॉल सिग्नल एनालिसिस करते समय क्या होगा सी ई का.
मैम कैपेसिटर विल बी शॉर्टेड.
कैपेसिटर विल बी शॉर्टेड, राइट. सो तुम्हारा ये क्या हो जाएगा, आर ई विल बी ज़ीरो.
ओपन. ओ सॉरी,
ज़ीरो हो जाएगा ना. तो यहाँ डायरेक्ट ग्राउंड हो जाएगा ये.
हाँ.
सो डायरेक्ट ग्राउंड होने से तुम्हारा गेन क्या होता है. एक नॉर्मल ट्रांजिस्टर का गेन कितना होता है. देयर इज़ नो आर ई. जी एम इंटू आर आउट, राइट. हमारे केस में जी एम इंटू आर सी है ना.
यस मैम.
जी एम हमें पता है कितना है, आई सी बाई वी टी. आई सी कितना आया था हमारा 9.9 इंटू 100 माइक्रोएम्प्स बाई 26 मिलीवोल्ट्स. तो जी एम कितना आ रहा है. तो उसके साथ गेन हो जाएगा 9.9 इंटू 100 बाई 26 मिलीवोल्ट्स माइक्रोएम्पियर्स इंटू 3.3 किलो ओम्स है ना. हाँ, 3.3 किलो ओम्स. यस. सो गेन कितना है. ये गेन इट टर्न्स आउट टू बी 125.66. okay, this is with the presence of the CE capacitance. अब विदाउट CE क्या होगा. विदाउट CE में क्या हो जाएगा, ये जो कैपेसिटर है ये प्रेजेंट रहेगा. मतलब ये कैपेसिटर नहीं है, तो कैपेसिटर है ही नहीं तो क्या होगा, दिस इज़ कम्प्लीटली गॉन. तो नाउ यू विल सी द इम्पैक्ट ऑफ आर सी कमिंग इनटू पिक्चर. ये यहाँ पे डायरेक्ट ग्राउंड नहीं है. तो इस केस में यू हैव टू फाइंड द गेन. तो उसके लिए कैसे करते हैं. ओह, दिस इज वी ई. So how will we find the gain? We have to write KCL and KVL. ठीक है. तो इसमें let's consider all the currents to be outgoing. तो इसमें अगर KCL लिखते हैं at VE, so we will find VE by RE plus V minus VB by R pi plus GM VEB. यहाँ पे VEB हो, VEB is 0, right. So V by 3.3k plus R pi कितना होगा? How much is R pi? Beta by GM,
Yes, ma'am.
which is 100 by GM कितना है? How much was the GM? यहाँ पे 2.626k. How much is the GM? Hello?
Yes, ma'am.
What is the values that we are getting? ये आ रहा है GM? Okay, maybe you can calculate later. तो अभी फिलहाल ये आना चाहिए. So let's move ahead with this. V minus Vp upon is GM. So GM will be no. So this R pi is coming out to be 2.626 kilo ohms, है ना? And GM will be like 100 upon R pi. तो ये हो जाएगा into 100 upon 2.626 k plus V minus VB upon 2.626 k equal to 0. Okay. R pi is 2.626 and GM को we have replaced using beta upon R pi से, ठीक है? So ये 2.626 you calculate, you'll get this value to be R pi. It's not GM, it's R pi. Okay. So ये करने के बाद we have the value of from here we have to find the value of VE in terms of VB, और VB और यहाँ पे अगर source है तो it will be VS, right? So one or the same thing. So we'll write it as VB or VS. So VE जो आता है it comes out to be 1650 by 1663 VB/VS, ठीक है? So either of one you can use, and then what we do is we write V out. V out is, यहाँ से देखो V out क्या होगा, it is the drop across this RC, right? So that is GM VB into RC. वो करेंगे तो V out आ जाएगा ना. So V out is equal to GM into VE minus VB into RC. So V out equal to GM, this factor 1650 by 1663 minus 1 into RC into VB. ये VB नीचे आ जाएगा तो V out by V in हो जाएगा. V out by VB is V out by V in, right? That is GM into 1650 by 1663 minus 1 into RC. ये क्लियर है? ये एक्सप्रेशन कहाँ से आया V out by VB का?
Yes, ma'am.
ये क्लियर है ना? So this V out by VB you will get to be 0.982 V out by VB. This is without, okay? Without capacitance जो gain आ रहा है वो इतना है. So what we have to find out ultimately is the ratio of gain with by AV without, which is actually equal to gain with कितना आया था 125.66 by 0.982. So this comes out to be 127.9. ये तुम्हारा रेशियो ऑफ गेन्स आएगा, ठीक है? विच इज दिस ऑप्शन ई. ये क्लियर है कैसे सॉल्व किया? सोल्यूशन में एनी डाउट्स?
Yes, ma'am. Clear.
क्लियर है ना? स्टेप बाय स्टेप समझ में आया ना?
Yes, ma'am.
Okay. Considering clear, this is clear to everyone, so let's move ahead. Now इसमें क्या करना है? Find input resistance for this given circuit, and by assuming the bypass capacitor is not present, that is the switch is open. If the switch is open मतलब ये RE रहेगा यहाँ पे, ठीक है? तो इसके साथ you have to find RN. So yeah, this is the small signal analysis, right? Small signal circuit ऐसा दिखेगा तुम्हारा. इसमें RE is not present, CE is not present. So considering like CE is open, so there is no impact of CE. तो उसमें you have to find what will be the RN. यहाँ से देखोगे तो what RN will look like. So RN कैसा दिखेगा? R1 parallel R2 parallel to, यहाँ पे R पाई है, ठीक है? इसमें जो करंट जा रहा है वो IB जा रहा है. ये RE है, इसमें जो करंट जा रहा है वो कितना जा रहा है? IC प्लस IB, है ना? इसमें IC प्लस IB is the current that is flowing, but this is coming into picture. So इसको कैसे लिखेंगे? R pi plus 1 plus beta times of RE. 1 plus beta क्यों? It's IB times 1 plus beta into RE, right? Clear है? सो यहाँ से आर इन जब हम लोग देख रहे हैं तो इट इज़ बेसिकली वी बी बाई आई बी विल गिव मी आर इन, है ना? इज दिस क्लियर? ये क्लियर है?
मम्मी 1 + बीटा कैसे आया था?
हाँ हाँ, देखो ये दिस टर्मिनल इज एमिटर टर्मिनल, राइट? और एमिटर रेजिस्टेंस के अक्रॉस करंट जो फ्लो होगा वो क्या होगा? आई सी प्लस आई बी होगा।
यस मैम।
सो उसमें से अगर इफ़ आई रिमूव आई बी, सो हाउ विल आई राइट 1 + बीटा आर ई? इसमें अगर यहाँ पे देखो, मैं लेट्स से लेट मी राइट इट लाइक वी बी जो है वो किस किस के अक्रॉस ड्रॉप होगा। यहाँ पे वी बी बाई आर वन करंट्स देखते हैं ना, वी बी बाई आर वन प्लस वी बी बाई आर टू प्लस वी बी अपॉन आर पाई प्लस 1 + बीटा टाइम्स ऑफ आर ई। इसके अक्रॉस देखेंगे तो आई बी होगा, और इसको अगर मैं ओके लेट मी राइट इट लाइक सम अदर वे विच विल बी क्लियर। देखो ये वाले पाथ में देखते हैं, आर पाई वाले में यहाँ पे आर पाई है ना? उसके बाद यहाँ पे देर इज़ आर ई, ठीक है? यहाँ पे वी बी है, इसमें आई बी फ्लो हो रहा है, इसमें 1 + बीटा टाइम्स ऑफ आई बी फ्लो हो रहा है ना? तो यहाँ से अब मैं लेट मी राइट द के वी एल। सो ये क्या हो जाएगा? आर पाई इंटू आई बी प्लस आर ई इंटू 1 + बीटा आई बी, है ना? सो इफ़ आई राइट इट लाइक वी बी अपॉन आई बी, सो इट्स लाइक इक्वल टू आर पाई प्लस 1 + बीटा आर ई, राइट? ये है। तो इतने रीजन का जो इफेक्टिव रेजिस्टेंस है वो कितना है? दिस। ये क्लियर है? वी बी बाई आई बी।
यस मैम।
अब इसको मैं लेट्स से आर बी नेट लिखती हूँ, ठीक है? लेट मी राइट इट एज आर बी नेट। तो मेरा आर इन क्या होगा? आर वन पैरेलल टू आर टू पैरेलल टू आर बी नेट होगा। So which is R1 parallel to R2 parallel to R pi plus 1 + बीटा RE। ये क्लियर है? Any doubts in this? Clear now?
यस
So yeah, if this is clear,
Ma'am,
हाँ हाँ
current direction will be reversed, right? Because the current is going as per this
yeah
force here.
yeah it's outside, so currents will be opposite, so इसमें negative कर सकते हैं, but negative resistance जैसा तो कुछ होता नहीं है ना, resistance is always like positive, तो mod में लेके चल रहा है।
Yes,
ऐसा
ma'am.
कुछ
I was just confirming the sign.
नहीं yeah, signs will be opposite, that is because this is a PMOS, so yeah, currents will be inward, all the currents will be inward and going out of base, so ऐसा होगा directions। तो आर इन क्लियर है ना? सो नाउ व्हेन यू कैलकुलेट द वैल्यू ऑफ आर इन, ये क्लियर है? ये एक्सप्रेशन कहाँ से आया?
हाँ यस मैम।
हाँ, सो इसमें सिंपली व्हेन यू पुट ऑल द वैल्यूज यू विल फाइंड आर इन टू बी 24.7 किलो ओम्स। ये क्लियर होना चाहिए, दिस इज़ वेरी इंपॉर्टेंट। तो यहाँ पे देखो आर ई का फैक्टर कितना इफेक्टिव होता है, इट इज़ 1 + बीटा टाइम्स ऑफ आर ई। मतलब ये बहुत बड़ा इम्पैक्ट डाल रहा है इनपुट रेजिस्टेंस में। कैन यू ऑब्जर्व दिस? अगर इफ़ देयर वाज नो आर ई तो इनपुट रेजिस्टेंस क्या होता है? आर वन पैरेलल आर टू पैरेलल आर पाई, राइट? बट यहाँ पे देखो, बिकॉज ऑफ दिस आर ई प्रेजेंस वी आर सेइंग अ फैक्टर ऑफ 1 + बीटा टाइम्स आर ई। 1 + बीटा मतलब कुछ नहीं तो मिनिमम 100 टाइम्स ऑफ आर ई। आर ई इज़ ऑलरेडी इन किलो ओम्स, then again it's 100 times, so This factor is hundreds of kilo ohms, which is a huge value. तो काफ़ी बड़ा रेजिस्टेंस और काफ़ी बड़ा इम्पैक्ट आ रहा है इनपुट रेजिस्टेंस में बिकॉज ऑफ आर ई, राइट?
Yes, bro.
So आर ई brings in that effect. It actually stabilizes the circuit, इसलिए आर ई is used. Similar to आर एस, जैसे MOSFET में we use source resistance, it's the same usage. जो यहाँ पे आर ई का है वहाँ उसका आर एस का होता है, ठीक है? Oh, okay. So what's the time? 10 minutes hai. Now coming to these questions. So now these four questions are based on MOSFET. Okay. So yeah, we have to solve for this MOSFET circuit. यहाँ पे you have to find gain V out by V in. What is the gain in a MOSFET when this type of configuration is present? What is the gain? Minus GMRD, right? है ना?
Yes, ma'am. Yes, ma'am.
Minus GM into RD. यहाँ पे KW by L is given 1 milliamperes per volt square. VTHN is 1 volt. Lambda is 0, it is very good. R1 is 60 kilo ohms. R2 is 20 kilo ohms. RD is 2K. VDD is 12 volts. So with this, first of all, GM find करने के लिए we need to find out what is the operation, mode of operation of this transistor, right? So सबसे पहले VG कितना होगा? VDD into R2 on R1 plus R2. Here is 12 into 20 by 80. 3 volts. तो आपका VG is 3 volts, VTH is 1, so VG is minus VTH कितना है? 2 volts, right? Okay, now let's see. So let's assume the transistor is in saturation for now. Assume T1 in saturation. तो करंट क्या होगा? ID is mean Cox W by 2L VGS minus VTH whole square. So ID is actually 1 milliampere per volt square by 2 into 2 का square. So ID is यहाँ volt square होता है 2 milliamperes. So now we know the ID. So let's find out what will be the VDS. What will be the VDS? VDS will be VDD minus IDRD, right? So VDS कितना होगा? 12 minus 2 milliamps into RD कितना है? 2 kilo ohms. So VDS is 12 minus 4 volts. VDS is 8 volts. And since VDS is much greater than VGS minus VTH, so yeah, transistor is definitely in saturation. ये क्लियर है ना?
Yes, ma'am.
तो जब ट्रांजिस्टर इज इन सैचुरेशन तब तो फिर सब सही है, हमारा VDS आया है वो भी सही है, करंट भी सही है, VGS माइनस VTH तो सही है ही. तो पूछा क्या था? गेन पूछा था. तो यहाँ पे अब व्हाट वी विल डू, वी विल फाइंड GM. सिंस दिस इज़ करेक्ट, सो व्हाट इज़ द वैल्यू ऑफ GM? GM कितना होता है? GM कितना होता है? म्यून Cox W by L VGS माइनस VTH होता है. डिफ्रेंशिएट करते हैं ना ID को.
Yes, ma'am.
तो ये कितना आएगा? 1 milliamps per volt square into 2. whole square. So GM is 2 millisiemens. RD is 2 kilo ohms. So gain कितना हो गया? V out by V in 4 है ना? So gain is 4. ये clear है?
Yes,
ये
ma'am.
तो simple था ना? Now let's so find the input resistance for the circuit shown. Okay. So इस particular circuit में you have to find the input resistance. Assume the coupling capacitor is shorted for the given small signal analysis. So what will be the input resistance? Zn will be R1 parallel to R2 parallel to infinity. ये infinity कहाँ से आया? Yes, ये infinity कहाँ से आया?
Capacitor
Gate
is
impedance.
गेट इम्पिडेंस. मॉसफेट का गेट इम्पिडेंस जो बीजेटी में यू वर फाइंडिंग आर पाई, राइट? दैट आर पाई इज़ अ फाइनाइट वैल्यू इन बीजेटी, बट मॉसफेट में इट्स इनफाइनाइट. तो जो गेट इम्पिडेंस होता है वो इनफाइनाइट होता है. सो इट विल बी सिंपली R1 पैरेलल R2. R1 कितना था, R2 कितना था? 60-20. सो R1 पैरेलल R2 कितना होगा? 60 इंटू 20 बाई 60 प्लस 20, that is 80. 60 into 20 by 80, 15. So Zin कितना आएगा? 15 किलो ohms. ये क्लियर है ना? बेसिक मैथ्स है, इसमें कुछ करना नहीं है. Now in this question find the output resistance for the same circuit. इसमें भी consider that capacitors are shorted. So if capacitors are shorted, output resistance क्या होगा? R0 है यहाँ पे. R0 कितना है इसमें? सी क्वेश्चन में दिया था लैम्डा इज 0. लैम्डा इज 0 होने से क्या होता है? R0 इज ओपन सर्किट, इन्फिनाइट हो जाता है R0. ठीक है. सो योर R out और I should say Z out is actually R0 parallel RD, but since there is no R0, Z out will be simply equal to RD, so which is 2 kilo ohms. ये क्लियर है? Z out कैसे आया, ये क्लियर है ना? इसमें कुछ नहीं करना था.
yes, ma'am.
क्योंकि लैम्डा 0 था. Now this question, so इसमें क्या लिखा है? For this capacitor, find the value of capacitor so that the frequency is 10 hertz. F is given 10 hertz for the capacitor C1. तो capacitor C1 के across अगर मेरे को चाहिए तो यहाँ पे वो क्या आएगा? How will I write the frequency? F equal to 1 upon 2 pi C1 into resistance कौन से होंगे? Yes, resistance क्या होगा यहाँ पे? C1 into जो कैपेसिटर उसके अक्रॉस जो रेजिस्टेंस है Zn, राइट? तो C1 is 1 upon 2 pi into 10 into Zn. Zn कितना आया था हमारा? 15 किलो. Yes. So it is 15 kilo ohms. तो C1 कितना आ रहा है? It will come close to 1 microfarad. इसको जब सॉल्व करेंगे so it comes out to be 1 microfarad. Okay? ये समझ में आया ना? इसमें कुछ नहीं करना था. ओमेगा इज 1 बाई RC, F इज 1 अपॉन 2 पाई RC, और जो C पूछा है उसके करस्पॉन्डिंग जो R होगा वी हैव टू कंसिडर दैट क्यूमुलेटिव R. तो यहाँ पे इसलिए Zn कंसिडर किया. क्लियर? एंड व्हेन वी डू द मैथमेटिक्स विल फाइंड इट टू बी 1 माइक्रोफैरड, which is option B. Yes. Now coming to the very last problem. So find the power dissipation of the amplifier across, like considering the biasing circuit as well. तो इसमें पावर डेसिपेशन फाइंड करना है. इसका मतलब यहाँ से जो करंट फ्लो हो रहा है, व्हाट इज़ दैट करंट? देयर आर 2 ब्रांचेस. सो व्हेन वी से पावर डेसिपेशन इट विल बी I1, और यहाँ से जो करंट फ्लो हो रहा है सिंस इट इज़ इन सीरीज विथ ट्रांजिस्टर तो ID विल फ्लो. तो power dissipation is actually VDD into I1 plus ID. Okay? So we will find I1, ID तो हमें पता ही था, VDD into I1 plus ID कितना आया था हमारा? First question में we found out ID, right? How much was the ID? 2 milli. So ID is 2 milliamperes. So now how do you find I1? I1 is VDD upon R1 plus R2, right? So that is 12 upon 80k, which is 3, 4, 20. Yeah. So its I1 is 3 by 20 milliamperes. So power dissipation is 12 into 3 by 20 plus 2 milliwatt हो जाएगा, because milliampere into volt will give you milliwatt. So when you calculate this, the power dissipation turns out to be 25.8 milliwatt. Is this clear?
Yes, ma'am.
Any doubt? Okay, actually I thought we won't be able to finish it, but yeah, luckily we could. So yeah, we are done with all the problems which I had decided for today. So all 14 are done. Any doubts in any particular problem, feel free to ask. Anything that you could not understand. MOSFET we went through very fast these questions, but because these questions were very easy, there was nothing to do. But still, do you have any doubts in these 4 questions, last 4 questions which we went through very fast? Yes, all of you, maybe Jyoti, Krishnapriya, Arjun, any doubts?
No doubt.
No, ma'am.
No doubts, right?
Very clear, ma'am.
Very clear. So yeah, I'll immediately upload the notes also. So just in case if you want to go through, you can go through the notes, and I'll upload the videos also. And yeah, as I said, if you want to practice more problems, so for basic level, the level in which we are going right now, you can follow the Razavi's book, and for advanced problems which we have not touched yet, but the problems containing current mirror circuits, differential amplifiers, OATs, for them you can follow the book which is advanced like analog CMOS IC design. There is this book, and if I am not wrong, the author is Razavi itself. So Razavi's analog CMOS IC design, you can follow that book. And yeah, also you can follow my lectures from last semester. They are in the same channel. So the channel that you follow for these lectures, there is another playlist which contains 12 to 13 videos. So you can go through that also for MOSFET based circuits. They are majorly MOSFET based circuits. So yeah, if there is no doubt, maybe we can halt this session over here and see you next week. Everything is clear?
Yes, ma'am. It was a good session, ma'am. I enjoyed.
Okay, thank you. It makes me feel very happy. But yeah, please try and attend. If you feel any doubts, you have any concerns, you can ask. Oh yeah.
Yes, ma'am.
Okay.
Yes, ma'am.
So see you next week then.
Thank you,
Yes.
ma'am, for the session.
Thank you.
Thank you, ma'am.
Thank you. Have a wonderful day ahead. Okay, see you. Bye.
You too, ma'am. Bye.
Bye, ma'am.
Bye.
Ma'am.
Thank you. Thank you for joining. Bye, everyone.